It is time for section 3.7, and you've all been waiting for it. Exponential regression. Exciting. So we're going to find those exponential equations, the best fit. That's going to be our regression. We're going to use the exponential regression to make predictions and decide whether the two types of regression that we currently have experienced, linear or exponential, is going to best fit the data. All right. So here we have a situation about the Ebola outbreak in Africa that was in 2017. And there was a conservative estimate that said that the incubation period was between, that the infection rate would be about 2, so doubling. And the incubation period is between 2 and 21 days. So we're just going to go for 15 days or half of a month just for the ease of this model here. And we'll make a prediction assuming that we're going to infect 2 people in about 15 days. All right, so with this in mind, the initial period, there was 1 person that was infected initially. And then we're going to say 15 days is about half a month. So half a month later, 0.5 is our half of a month or our 15 days. That initial person infected 2 more people. Okay, so that person infected 2 more, so that brought us to a total of 3 infections once I added those together, right? Because that in first person got 2 more people infected. Now I have a total of 1 plus 2 is 3. Okay, so the initial person was not able to infect anyone more. They got better, but the 2 new infections, those were able to infect 2 more people each. So I got 4 new infections. So if I add up my 4 plus 3 here, I get 7 total infections. Okay. Then again, those 2 people recovered, didn't infect anybody new, but these 4 people were each able to infect 2 more people. And that's why I have 8 more infections going on. And we can see this pattern. Again, our 8 plus our 7 already infected gives us the 15. So we're going to keep this up and we're going to make a table for the number of people infected over the 5-month period. Okay, those 8 double to 16. 16 plus 15 is 31. This 16 is going to double to 32, and 31 plus 32 is 63. This 32 is going to double to 64. 64 plus 63 is going to be 127. This 64 is going to double to 128 new infections. 128 plus 127 is going to give us 255. Doubling 128, that gives us 256. I'm going to add it to the 255. That's going to give us 511. Then this 256 doubling is going to give us 512. And 511 plus 512 is going to be 1,023. And the 512 people are going to infect another 1,024 people. Adding on to the 1,023 people will be 2,047 people. Okay, so we are going to take a look at this scatter plot. We're going to plot this in Desmos. When I plot this, we're going to plot the month data, the time data, and we're going to plot the total number of infections. So we're going to plot the top and the bottom rows. We don't need to plot the middle row. That's just the number of new infections. We're not interested in the number of new infections. We're interested in the total number of infections at the end of the month or month and a half or whatever we've got going on in this situation. Okay, so we're going to plot these 2 items into our Desmos chart. So I've got my values entered here, and I'm going to zoom fit on the data set so we can see all of the data in a more appropriate window. Question number 3, does the scatter plot indicate a linear relationship Well, no, because I do not observe a straight line pattern. This is very much curved. And we should observe that it very much does look like what we would expect an exponential function to look like. So just for comparison over on our side, if we had expected linear, we would have seen a steady increase. But if we're expecting exponential, we would see slow increase followed by rapid increase. And that's the shape that I very much see here from this data set, the slow increase followed by the very rapid growth that is characteristic of the exponential shape. So we will note that here also, that no, because the growth rate is not constant, or the growth rate of change, the growth is not constant. Instead, it seems to be increasing more rapidly, and that's going to indicate exponential. Okay, so now we're going to go ahead and do the model. When we do models, if we did a linear regression, just going to put it up here just to remind ourselves that we already know what we already know about regression. We would have done y1 is approximately mx1 plus b, and that just came from knowing what a linear function looks like. And obviously, as we can see here, that a linear model is not going to fit the data very well. It does not follow the shape of the data set. But a reminder, if I wanted the model linear, I just had to remember what a linear equation looked like, that it looked like mx plus b, and that I would change x and y to x1 and y1 to match the table, and I'm going to use the tilde key for the approximate. So I can do the same thing with exponential. For an exponential function, I know that it's going to be of the form y equals a times b to the x, or ab to the c. In this case, we're going to start with y1 approximately ab to the, and our input variable from the table is x1. Let me go ahead and get rid of the linear, which we do not need in this case. Look at just the exponential model. All right, so you can see that your exponential model is doing a wonderful job of fitting this data set. It's very close to the data. And you can observe that because the R value here is 1 as well. Now, before we write down some of these values and before we talk further about the results of this exponential regression model, I will note that there is this box here that says something about log mode. So I'm going to undo real quick and notice that there's not a box like that for the linear function. We're only going to see these in the exponential and logarithmic models we make. So I didn't have to talk about this before in terms of linear. So there are two different ways that the regression parameters, the A and B values here, can be computed behind the scenes. One of them involves shortening the computation, and that would be the log mode option. That was necessary on the handheld calculator devices, like a TI-84, because they're not powerful enough to do the calculation with some of the full values, especially when these grow very rapidly. Some of the numbers are going to be quite large inside of the calculation. And so log mode is a way that we were able to simplify those calculations. Now, that does slightly change the model. Doesn't make it any more or less good. They're both good, but it does slightly change the parameters. So I'm actually going to copy and paste this so we can compare them. And so I can see the model with log mode on and without log mode on. So they look very close during the model, but there is a little bit of difference I can see over here on the side. And in this particular situation, it looks like I'm probably a little closer to the data if I do not use the log mode box than I am if I do use the log mode box. That's not always the case. It could be the log mode box looks a little better, but because the log mode box, checking that does simplify some of the calculations, there is a chance that there's a little bit more of compounded rounding error in this. So I want to first of all express that there are two different models that we can compute. The parameters are slightly different. In the log mode box, my parameter is a little lower for A, 1.3 compared to 1.97. And my B value parameter is a little higher, 4.4 compared to 4.0. So we always need to ask ourselves, which of these models do we want to use? And For the purpose of my math lab questions, for the purpose of answering homework questions, we're going to need to check the log mode box. We need to check the log mode box because they want to make sure when they code the questions in the software that anybody can answer the question regardless of the device they're using, regardless of whether they're using decimals for the question or a calculator for the question or Excel. You can do these kind of computations in Microsoft Excel as well. And that's also going to be using the log mode option. So we're going to stick to the log mode box when we talk about questions that are going to be things that tie into homework. We're just going to try to get in the habit of always using the log mode box so that we don't have to worry about when to use it and when not to use it. We'll try to be consistent and we're going to use it so that we don't forget to do so when it comes to homework questions, my math lab in particular. Those questions are built to be able to be answered no matter what calculator device you're using. That's our reason for using log mode for right now. So I'm going to note my model in log mode and I'm going to write it down. I can see that my A value with the log mode box checked is 1.365 and my B value parameter with the log mode box checked is 4.42973. And I just realized I must have done something small because these values don't match the ones from the calculator. So let me look up here real quick. I found that I accidentally mistyped one of my data points. I apologize. Remember, it was supposed to be 1 month and 7. I accidentally just mistyped this one thing. Everything I had said down here about the two models, that was still appropriate. The parameters changed when I updated my data to the correct value, so I'm sorry for that. Let me go ahead and rewrite my A value with the log mode. It is 1.41367, and the B value with the log mode is 4.39264. One tiny little digit there, and we do see a bit of change between these values. So I just noticed that because I was trying to compare it with the values here in the table to make sure that the A values that we were able to get from our decimal regression and the B value we're able to get from our decimal regression does exactly match the values up here. Now, again, I'm going to double check to make sure I haven't typed anything in incorrectly again, because I'm not seeing the same thing after the 4 decimal place, or hold on, 3.39264. Oh, I just see more places. So I see more places on the calculator screen. It looks like these are rounded right here, and there's a few more places on the calculator screen. If I did need to have those additional places, well, as long as I don't have A and B defined twice, I can ask for them. So if I get rid of the non-log mode regression, I can type the letter A and I can get more places on that A value and we can compare that with what we see down here. And the same thing with our B value and we can compare with what we see down here. And again, you should be able to see that, yes, I am getting the same exact thing in the calculator screen if I did need that many places. For the most part, though, we're going to need just 4 or so places, and Desmos is giving us the 4 places that we'll need for each of these and more. All right. So I'm going to pull this screen off just for a moment so I can write on the bottom. Those are the parameters. The parameters are not the equation. We want the actual model, the equation. So we're going to put that back together. Y equals 1.414. I'm going to use 3 places on my A value times 4.3926 to the x. I'm going to use 4 places on my B value. It is more important generally to keep more places on the base because the base is the value that gets repeated, and the more error you have in your base value, the more likely that error is to compound. The A value gets used just once, multiplying it by the end result here, and so it's not as necessary to have as many places in your A value. If you're told how to round it, if it says 2 places, you'll keep them both at 2 places or whatever it is. But in general, I would keep 4 on my B value unless I was specifically told to have less there. Okay, so we're off to a good start. I already made a mistake with one of my numbers, typing it in. Let's see if we can do a little better here on the next page. All right, sketch the graph of the exponential model, add it to the scattergram. Well, that happens automatically when I graph things in Desmos, so I don't have to do anything extra. I can see it already on the scattergram, and I can tell that it's a good fit, and I can also see that it's a good fit because the r-squared value is 0.996. Though we can see r-squared and r, usually we talk about r-squared if the model is not going to be linear. So we'll talk about the r-squared value here at 0.996 as being quite close to 1, and so this is a strong correlation between the data set and the model. So I'll make it a note, my r-squared value is 0.9966, and so this is actually very strong coefficient of correlation. This is very close to 1. All right. Next, what is the practical domain of this function? So the practical domain is going to tie into the situation. So we're talking about months since the first person got infected. And so prior to 0, nobody had been infected. So it would not make sense to go into the negatives here. So our practical domain is going to be from 0 up to something. And we've already established that we can have decimal values half of a month. So we could extrapolate that we could have a quarter of a month, and we'd be able to connect values in between these. So we don't need to list them. We don't need to go discrete. We're going to say this is a connected or continuous situation. Now, we have our chart here going up through 5 months. We might be able to predict a little bit beyond that, but usually the general idea is you go about half again the width of the data set. So if half the width of the data set is 2.5, I might only go 2.5 more months. So let's say we go up to, say, 7.5 months. If I wasn't using increments of half, I might have said only 7, but we'll see what we can do with a prediction of up to 7.5 months. That half again, the width of the data set's not a hard and fast rule, but the idea is that exponential models break down very rapidly. So you can't go too far past the edge of the data set, and half again kind of gives us a guideline of how we could start to think about how far would be acceptable to go. What is the y-intercept? Well, I know that my y-intercept is related to the a value, and so it's always the ordered pair, 0, the a value. So my a value was 1.414 from the model. How does this compare with the actual value from the table? In the table, 1 person had been infected initially. We're saying that 1.4 people had been infected. So it's not exact, and we may argue that technically 0.4 of a person can't be infected, but maybe they were on the way to catching it. I don't know. There might be some way that we can interpret this, but it's close, is what we're going to say. What this means is initially 1.414 people were infected. And how does this compare? We would say that it is close to the data set. This is close to the actual value. Can't get much closer to 1 than 1.4 in terms of it's still between 1 and 2, and it does round down to 1, so it is very close to the actual value. All right, so the procedure that we used to develop the exponential functions in the previous sections is different from the one that we use here when we're using regression. And as they're saying here in linear regression, we can calculate the coefficient r, but for the exponential, it's really the r-squared that we're going to start to worry about. Okay, so does the value of r-squared, I already talked about this, I guess I jumped the question here. The r-squared value of this one is the 0.9966. Does this confirm what we said in 3, which was, or problem 4, what we said up there? Does it confirm? What's problem 3? Does it confirm that we think the exponential is going to be a good fit? Problem 3 was the one where it says, is it linear? No. We thought it was exponential. Yes. And so this should confirm that exponential is a good fit. Now we're going to use our exponential model to predict the total number of people infected 1 year after the initial infection. So we're going to use, since we're talking in months, we're going to use t equals 12. So we're going to have our 1.414 times 4.3926 to the 12th when we put 12 in for the power. I'm going to go ahead and just type my function as a function. And then I'll be able to call that function at 12. So round the nearest whole person, we are getting 60,741,791 people infected. Now, that is very likely to be an overestimate since it's far from the edge of the data. Our data had only gone up through the first 5 months, and so 12 being far away, this is likely to be an overestimate of the actual number of people. I don't have the data for 12 years or 12 months afterwards, but we could look it up and find out how many infections there were. Next, they would like us to use the function to write the equation that can be used to determine when the virus will first reach 2 million people infected. So this 2 million people is an output. So we would graph y equals 2 million. And then we'll look for the intersection. Because of rounding my a and b values, over here I can see that the function without rounding or with holding more decimal places is a little bit higher than the function that has the rounded values down here. So if you're working on a homework question and you already rounded, you're going to want to make sure you turn off the actual regression so that you're having the expected amount of rounding error in your function here. And actually, did I just skip a number? Totally did. Didn't even type my 9 there. That could be part of why I was seeing so much error. Yep. So I apologize. Apparently I'm having an off day, but I hope you'll forgive me. I'm going to keep this going here. I didn't type this in right. So 72,964,111 people infected. Sorry for your notes if they're going to be scribbled out and looking like mine, but we can do this. All right, so I'm going to go ahead with the 2 million. I need you guys to be able to talk to me right now so I can make sure I'm typing all of this correctly. Now, 2 million is very large, so zooming out is not going to be very effective. I'm going to go ahead and take the Y max and pop up to 3 million. So I can find 2 million right there in the middle, and then I'll be able to zoom to the side from there. So our prediction for 2 million is that ordered pair right here at 9.57. And so our prediction is that it will take 9.5 or 9.57 months for 2 million people to be infected. Now, if you're asking or thinking about our confidence level in that prediction, the data is very far away from this point, especially vertically. You can't even see that there's any growth right here. They look like they're flat, although they're not. Remember, this was at a height of 1. This one over here was at a height of 1,023. But when you compare that to 2 million, there does seem to be quite a large gap in those values. So it is extrapolated. It's past what we had decided was going to be in our practical domain. And so reasonable, we cannot be reasonably sure that this is accurate. We're going to have to make sure that we know this is an extrapolation. So we don't have a lot of confidence in this prediction being truth because it's far from the edge of our data set. So we'll just make a note that both of these are extrapolations. They're wild guesses. They're far from the edge of the data set. And both of these were extrapolations. Oh, now I'm reading the directions for B and C and D, and I'm realizing that what I did here was actually C and D. What they had wanted us to do for part B was not to solve it, but to write down what I would need to do to solve it. So in part B, like I noted, if I paid attention, I would have more space right here. That this is an output value. So since that's an output value, we're going to take that 2 million as an output value, and we're going to plug it in for y in our function. And so this is all they really would have had me write down for part B, that this is an output value. Then they would have us do the graphing part, find the intersection point in part C. They would have us write our sentence about what it means in part D. See if I can get my stuff together here for the next one and do things in the correct order. All right, go ahead with our data set here. Let me get rid of everything. We're looking at some bacteria grown over a period of 6 days. We start with 600 items, then there are 710 items, and so on. So let's look at the scatter plot of this data. And if I look at this, I notice that it's a lot straighter than the last data set, but it's not a constant rate of change. There is that bowing, that curving a little bit slighter than before for sure, but that shows you that the growth here is a little less than the growth at the end. So these only grew by 110, whereas these grew by 300. So I am growing at a more and more rapid pace as we go on. So this will be an exponential function, but it's likely to have a lower value for its base than the previous one. Okay, they would like us to find the exponential model for this in part 8a. So y1 is approximately a times b to the x1. This is a beautiful model, fits that data very tightly, has an r squared value of 0.9993, so it's a very strong correlation. Oops, come back. There we go. Just want to shrink it a little bit so I can see the numbers at the same time as I'm writing them for 8a here. So our model, n for the number of bacteria, so n of t, is going to equal our a value, which is 597.314, times our b value, which is 1.18909 rounded to that 1 right there, if I'm trying to stick to the 4 places that I had mentioned earlier. Okay, so sketch the graph. I've already done so because it happens automatically in decimals, not so in the calculator. And what's the practical domain of this exponential function? Okay, well, I've got data for up through 6 days. If I go half again the width of the data set, that'd be 3 more. I really wouldn't want to make any predictions past 9. Even 9 is going to be pushing it. But we will say that our practical domain is going to be about 0 to 9. And then once we actually make predictions for 9, we can see how far it is past the edge if we believe 9, but we wouldn't want to go past that for sure. So somewhere in the 0 to 9 range, we can't make predictions before 0 because you didn't put the bacteria in the culture yet, so not starting to grow it. So I'm not going to go into the negatives, but I can go past 6 a little bit unless I threw it away. I don't know if I threw away my bacteria culture or not, but it's still going to grow for a few more days, assuming I'm leaving the experiment running. All right, what's the vertical intercept of the graph? Well, I know my A value is the y-coordinate of the vertical intercept, so I know that I get 0,597.314. And how does it compare to the actual value? It's pretty close. Our actual value was 600. I have 597, so I'm very close. It's not going to be exact. That's okay. It gives us a pretty close prediction. There's going to be a little bit of error in every single prediction because we didn't have an r-squared value of exactly 1, but we're quite close. So 597 is close to 600. Now, we have to believe that it really is close. You can't just say, oh, 500 is close to 600. Then I would be like, hey, that's a little off. But that's just 3 bacterium away. Bacterium are so small, I could have just miscounted them, right? It's pretty close to the actual value. So our model is not perfect, but fairly decent. What is the base of the exponential function? Is it a growth or decay factor, and how do I know? All right, well, I know that it's a growth factor because it is larger than 1. So I'll say that first. It's a growth factor. B equals 1.1891. And how do I know that it's a growth factor? That's because this is larger than 1. So B is larger than 1. What is the daily growth rate? Okay, this is a daily model. So the growth rate, R, is going to be found from our growth factor. So we'll take R equals B minus 1 as a percent. So if you subtract 1, that would be 0.0, 0.8, need to read my numbers here, 0.1891, which converts to 18.91% per time units, which are day. Now we're going to use this model to predict the number of bacterium in the culture after 10 days. So we're going to find N of 10. So I need to type my model. So I'm going to keep the screen down here for a second as I type in my N value or my A value and my B value. All right, so I've got N of 10 equals 3,375 point. These are bacterium. So, I mean, I'll go for 0.9 bacterium, but I don't need to keep too many decimal places when I'm trying to predict the number of bacterium. I might say 300 or 3,376 bacterium, but maybe there's one bacterium that's in the process of splitting into 2. It just hasn't quite made it all the way. So that's maybe the 0.9. So then we want to compare this value right here at 10. It's not right at the data set. It's a little ways away. By the way, the number that's showing up right here is slightly different because I still have both models turned on, and we turn this one off, so we're making sure we get the same rounding that we had when we did the model. So that should be matching with what we saw from N of 10. And unlike the previous one, I mean, it is far away from the data set, but the data is not all flat in comparison. There was a lot more error when we made the data predictions for the Ebola model, just because we were distance-wise a lot further away from the data set. I still think this is extrapolation. It is certainly extrapolation. And near extrapolation would be in this realm, this is mid to late, I mean, late's obviously much further is going to be considered late, but this is still extrapolation. So I would question the validity of it based on how far it is from the data set, noting that the height difference between the first point and the last point is 900, and this is more than 900 away. It's thousands away. So I would question its validity. So we will note to ourselves again that we have some extrapolation here. All right, so part B, use the exponential model to write an equation. I'm going to follow my directions this time. To write an equation to determine when the number of bacteria will reach 10,000 bacterium. We'll solve it in a minute, probably on the next page. So if they just want me to write the equation, they're trying to make sure I know what to do with this 10,000. This is an output value, so I'm going to plug it in for the output side of the equation. So I would do 10,000 equals 597.314 times the 1.1891 to the t. That's the equation that I need to solve. They want us to write this equation down because as we get into cluster 2, we're going to practice solving this equation algebraically. But for right now, in section 3.7 and for cluster 1, we're going to go ahead and solve this graphically. So they're going to ask us on the next page to do that. When I solve this question graphically, I do have to graph the output value, y equals 10,000. And I can zoom to find that because it's not too far away from where I'm already at window-wise. And I can see that I have this intersection point right here on my graph of 16.27, 10,000. You can also compare with their values they have down here. And again, rounding is going to matter depending on what they have typed in. If they have the NFT model, where we've rounded to 3 places and 4 places, or if they have different rounding. It looks like, I don't know how they rounded theirs. If they kept it to just 3 places or something, that's why they have a slight discrepancy in their number versus ours based on the rounding used. So when you're doing a homework question, it always tells you how to round your function. You'll make sure to round it and then use that rounding for the rest of the question, so you'll be getting your answers to match whatever they have directed. Okay, so our interpretation here is going to be that after 16.27 days, there will be 10,000 bacterium. And they do ask me, how confident are we in the prediction? And I'm going to say that we're not very confident because look at the distance between that point and your data set. The data is all chunked down here and we are far away from that. So we are not confident, as this is extrapolation. So if you had a job counting bacteria and your boss was like, how confident? You're going to be like, no, I'm not confident. In order to be confident, what you would have to do is run the experiment for more days and count up the number of bacterium over a longer period to gain more confidence in that prediction. So we're not confident that it's only going to take 16 days. Run the experiment longer and do some more tests to find out. All right, what is the doubling time for this exponential model? Okay, to find the doubling time, we need to double from the initial value. I'm going to zoom back over on the data set. The initial value was that there were 600 bacterium. And so if we double that number, we can find out how many or how long it takes to get twice that many bacterium. Now, we do have a little discrepancy in the fact that the model shows a prediction of not exactly 600, but remember of 597 bacterium. So according to the model, it's the 597.314 bacterium that we should be doubling to find the doubling time for this model. They're not asking me specifically for the doubling time of the bacterium. they are asking me for the doubling time of this exponential model. So I do want to use the 597.314 as the value that we're going to double. Okay, so let me get rid of the 10,000 prediction, and I want to find out when I am not at 597.3, but at twice that, when I have doubled. I'm going to turn off the data point so I don't accidentally click on my data point, and I'll find out that it takes 4.002, or about 4 days, even if I round to 2 places, about 4 days to double. Okay, so just some notes off to the side that we have our exponential function. We have our initial value at 0,597.3. And then if we graphed y equals twice that, y equals 1,194.6, that will give us this new ordered pair of 4.002, 1,094.6. That's the work that we did here to get to the conclusion that it takes about 4 days for the model to double, for the number of bacteria to double. Now, if we compare that to the data set in this case, we are going to be validating that prediction. Just noting over here, they do have a data point for us at 0,600, and 4 days later at 0,1200, we have doubled. So in terms of the data, it did take 4 days for us to double. In terms of the model, it took 4.002 days. So perhaps I'm a little more precise in terms of the model of keeping those 4.002, but it's very close to 4. We just rounded it to 4, even to 2 places at 4 days to double. So when they are asking me to estimate this in terms of the model, I'm going to double the A value like we had done in the previous section to talk about doubling time for the model. We're using the model as a predictor of what's happening in the bacterial population. Last example, looking at a decreasing exponential model. I've got some data here to type, and we have year values. And we need to talk in years since. They tell me down here to use years since 2005. If they hadn't told me somewhere, that's probably what I would have chosen, since 2005 is the first year. We never type in whole years. So we're going to do 0 for 2005, then it was 3 years to 2008, 7 years to 2012, and 13 years to 2018. So the numbers that we're going to type in are going to be our 0, 3, 7, 13, and then the cost of the television. Don't ever type a full year value. Even if their data is in years, you got to change it. Still getting some of those tables coming back on Desmos projects that have year values in them. So I want you to fix that if you have been doing it. Okay, and let's take a look at this data set. Okay, so it's decreasing. A straight line wouldn't be bad, but you see a little bit of curve here? It looks like it decreased faster at first, and now the amount of decrease is kind of slowing down. So let's take a look at how an exponential regression would fit this. So y1 is approximately ab to the x1. Look at that little curve I was talking about. So this model fits it very well. This is my oh shit moment when I realized I didn't push the log mode button box in the entire last question. You're probably wondering why. I don't think I did. I'm going to do that now. I forget sometimes. It's okay. So now I remembered to push it. And this is the model that would match the calculator screen. If you don't remember to push it, you've got yourself a very nice model. Some say a better model, but it does not match the ones that the calculator devices are able to give you. So I pushed it this time, and I have my logarithmic model, my exponential model in logarithmic mode, and I'll find the coefficients here by scrolling down. Very nice model here. And what are we doing? We are writing this as, they don't really say. I'm going to call it A for the average selling price of T equals 924.014 times 0.891, and then it looks like 89, so we'll make that to a 9, and then to the T. 0.8919 to the T. Sketch, done. What is the base? Is it a growth or decay factor? How do you know? Well, it's smaller than 1, so it's a decay factor. The decay factor is 0.8919. I know it's a decay factor because it is between 0 and 1. What's the annual decay rate? So I'm going to take my rate is going to be 1 minus my decay factor. Unlike the last time they asked me this, where I could just subtract the 1 in my head by covering it up, I can't do that here. So I will actually type in the 1 minus 0.8919. So I get 0.1081, or 10.81%. One of the reasons that we keep 4 places when we do our growth and decay factors is because it's really only 2 places once you consider your growth or decay rate. If I'd only kept 2 places on that, I'd have no accuracy, no precision on my rate. So I only have 2 places on my rate as it is. That's why I keep 4 places on my factor. And then I should put per something here because rates are always per whatever the units on the input are. In this case, year. So I'll put year. And just for some extra words here, I can say this is a decrease because I know the decay factor. So we're decreasing by 10.81% per year. Does the graph have a horizontal asymptote? Why, yes, it does, because it's an exponential function and they all have horizontal asymptotes. The horizontal asymptote for almost all of the exponential functions, especially those in standard form, ab to the x, is y equals 0. So the asymptote for this one as well is y equals 0. So what does this mean in context of the situation? So we're talking about the average price of a 32-inch television. So it means that as time goes on, the value of the television decreases towards 0. There we go.